Hi, my name is Mohammed Abdulaziz, and I'm a Vanier Scholar at Carleton University. Throughout this tutorial, we're going to go through different aspects of biomedical signal quality. The title of the presentation is Signal Quality from Wearables to Hospitals. Today's instrumentation in biomedical engineering has been throughout the years as a Holter monitor, as an example, to record ECG or to record different signals. So they've costed thousands and thousands of dollars. And so we expect them to produce a good quality signal. However, as the explosion with IoT, and especially IoT in wearable devices, we get something more on, as example on the right, which is a watch that's also designed to record biomedical signals or biosignals and is able to produce diagnostic information. However, this watch is only in the hundreds of dollars, so we're not expecting it to have as much quality as the full-on Holter monitor. Additionally, beforehand we had experts using these devices and putting them on the individual or the patient. But now we have regular individuals and even ourselves, non-experts, using these devices in order to gain information. So we're also not expecting them to install them properly and to get good signal quality out of it. Now, that actually brings us to a good point is, what is signal quality? And this is actually a very hard topic to define because signal quality depends on the application. So I will have my own definition and you will have your own definition depending on your area of work. But for me, a signal quality is whenever I have enough information to get to the diagnostic, to the decision that I need. The objectives of this tutorial is to identify the sources and the types of contaminants in biosignals, and also to identify the different aspects of quality, of signal quality. A quick refresher, biosignals, electrocardiogram ECG is the signal that's generated by the electrical activity of the heart and is typically used in order to diagnose different types of cardiovascular diseases such as atrial fibrillation or myocardial ischemia. And it has a very distinct shape such as PQRST. Second signal is EEG, which is brain signals, electrosonography. And it's used in order to diagnose epilepsy. And as you can see, the signal is quite hard to discern whether it's good or bad because it doesn't have very discerned patterns. The third is EMG, electromyography, and it's also a signal that's generated by the muscle. However, it's not the cardiac muscle, it's the skeletal muscle. And it's used for different aspects in the medical field, such as diagnosing carpal tunnel syndrome. And again, the signal has this quite random shape to it, so it's quite hard to discern whether it's good or it's bad. Finally, we have PPG, which is it's an generated by an optical sensor, and it's generated through the blood flow. And it's there in order to monitor heart rate and blood flow, and for diagnosing of atrial fibrillation and other cardiovascular diseases. Now, you can also see that it has a very nice shape, so we might be able to discern some information from it in terms of the quality. There's different contaminants, and this is a very nice table that summarizes it. It can be divided into measurements, into instrumentation, and into interference. So the measurements is that what you're getting as you are measuring the signal. The interference, the instrumentation comes from the instrument that you're using. And finally, the interference is from outside sources. So motion artifact, baseline wandering, and skin stretch reflexes are usually there because the subject is moving, or you're getting some noise as the point of contact of the device on the patient is getting some motion into it. Instrumentation, on the other hand, is when you're reaching the limits of your own devices that you're using to collect, and as an example, that would be amplifier saturation. And finally, interference is something from the outside, so as an example, power line interference or RF interference and crosstalk. Here's an example of how baseline wandering, it's a very slow type of noise. Here is an example of motion artifact. Has a bit quicker than baseline wandering, and it could be very destructive for the signal. And finally, we have power line interference, which you get this sine wave into the signal that you're trying to collect. Now, in order to try to discern these different types of contaminants and noises and how to deal with them, we need to talk about signal quality. And signal quality could have multiple aspects, and I like to think of them as different perspectives. So we have detection, identification, quantification, and mitigation. And we're going to go into them shortly. detection is essentially saying whether or not a signal is clean or bad, without any trying to figure out which type of noise is there, without trying to figure out how much, and without trying to figure out how can we deal with it. It's just simply saying that's good or that's bad. And detection is typically used whenever we're doing long-term monitoring. So in long-term monitoring, a patient or a doctor is trying to collect data from a patient that could be gone for whether it's days or weeks or even months. An example would be Holter monitor. So it doesn't make sense for us to collect that data and try to remove any noise when we know that we're going to collect more data later on. So simply saying whether or not that signal or that biosignal has noise in it or not, or contamination in it or not, could be more than enough. So there has been a lot of research that has been done in this area, and this table summarizes some of the techniques that are in detection. We also can see that the different techniques can be divided into 3 subcategories. We have fiducial-based, non-fiducial-based, and deep learning. A fiducial-based technique is used to identify different aspects of the signal. As an example, in ECG, we have the P, Q, or ST, so it's used to identify, as an example, the R wave. So that would be considered as a fiducial point. And here's some papers on it, where the QRS complex or the R to R interval has been used in the ECG in order to determine whether or not it has any contaminants. And the way you could do that is either through using templates that is based on the fiducial points and trying to compare it with the signal that's coming in, or it could be by simply trying to discern whether these fiducial points are where they are. If they're in a different location, which means that they're moving around and they shouldn't be there, that typically means there's noise. And we could also see that we achieve pretty good performances by such as sensitivity and specificity that are well into the 90s. The second subcategory, which would be non-fiducial based. And in non-fiducial based, we're actually not trying to identify any type of points or landmarks in the signal. More or less, we're trying to, usually these techniques would actually simply use power or some sort of a ratio in order to determine whether there is noise or not. So we can see there these different types of techniques. So Fraser decided to extract 31 features that none of them are dependent on any landmarks and simply on fiducial points, and fed them into a machine learning algorithm, and was able to achieve sensitivity over 100% for SNR that's less than 0 dB. Did ratios of power between different bands. So in ECG, we know that a specific band contains a lot of power. So we know that the power of this band compared to the rest should be higher. And depending on that ratio, we can determine whether there is noise or not. And finally, Tobon did the modulation spectrum based quality index. And that achieved a very high correlation between it and between the actual signal to noise ratio of the signal. Finally, we have the last subcategory, which is deep learning. And in deep learning, we're not doing any assumptions about the signal. We're simply giving it to algorithm and asking it to discern the patterns for us. And we're gonna go give just an example of one of the techniques, and let's start with, let's do a fiducial point. And here, Orfandio decided to propose a template matching technique in order to determine the presence of any contaminants in whether it's ECG or PPG. And the algorithm, because it's only detection, only labeled the data as either good or bad. And here's a more or less like a walkthrough through the algorithm. You can see it goes through different fiducial points. As an example, detecting the HR, which requires detection of the R peak, and then depending on certain thresholds that have been set, to either say it's a good or a bad signal. The very cool part comes at the very end, which is the template matching. And in here, they created a template based on the signal. So the way that works is you detect the R peaks throughout the signal, and then you overlay these R peaks and average them out, essentially doing an ensemble averaging. And by doing an ensemble averaging, you generate a template of the signal, and you expect that template to stay the same. So if it's a signal that has very discerned fiducial points, such as ECG or PPG, you're expecting that shape to remain similar because, well, simply our hearts beat the same way, and hopefully doesn't change over time because that would be indicative of certain diseases. But in the short term, we expect that template to stay the same. So you would color it between the template and the signal. And then from there, you'll be able to discern whether or not there is contaminants, because if the correlation is low, that means that the signal or there's a contaminants in the signal. And you can see that doing this ensemble averaging in order to end up with the template could work whether there is noise or there is no noise, or sorry, contaminants or there is no contaminants. The results are actually quite interesting and very promising. So they used PhysioNet, a data set from PhysioNet, which was, PhysioNet is one of the biggest databases of biosignals. And the sensitivity and specificity were quite high, in the higher 90s for ECG and for DPG. The next step is, okay, so we decided and we found out that there is noise or there's contamination. And by the way, I've been using noise and contamination interchangeably, and for me they mean the same thing. But we found out there's contamination in the signal. The next step, well, let's try to identify it. And that's important in order, it gives us insight on what sort of techniques we should use in order to mitigate that noise. And by the way, we're going to get to the mitigation later. So here's an example. Here's a clean signal. And now we're trying to decide whether or not there's noise. So in the detection, we said, oh, there is contamination or there is noise. And now we're saying it's motion artifact. There's actually not a lot of techniques that has been developed in that area. The two techniques that I was able to find, they were mainly based on machine learning and so essentially extracting features and giving them to a machine learning algorithm. So here, as an example, McCool for EMG, he extracted 7 features and was able to discern the different types of noises. I actually did some work in that area, but I did it on ECG, and I extracted 53 features, and in the 53 features, used it in order to discern the type of noises and different combination of noises, and was able to achieve precision and recall of 0.81 and 0.70. So let's go through the technique that has been developed by McCool. So McCool proposed a machine learning approach to identify ECG, motion artifact, power line interference, and amplifier saturation and amplified Gaussian noise in EMG. So you could already see some difficulties there, because white Gaussian noise is actually quite similar to EMG in its characteristics, so it could be hard to discern. That has been coupled with the features that was extracted was coupled with an SVM. Here's how the essentially the system looked like. So we had the EMG signal coming in, 7 features were extracted, and you'll notice that most of the features, none of them are really fiducial. It's more or less different ratios of different pieces of information in the signal to each other. So we have signal to power line noise, signal to motion artifact, and this is based on the different bands in the signal and or doing ratios of them, and then the classifier, and then finally the classifier, which is an SVM, and finally you have the classification result. Here's an example of how the signal is going to look like, EMG is going to look like with noise. You can see that additive white Gaussian and clean EMG are very similar. You notice that motion artifact and ECG actually does have very discernible changes in the patterns of EMG. And then finally you have the power line noise and amplifier saturation, and you can see their effect on the EMG signal. The results were quite promising. So you could see here, the green is the amplifier saturation, red additive white Gaussian noise. Then you have ECG in the pink, power line noise in black, and then motion artifact in the blue. So on the left-hand side is simulated EMG with the noise added to it, and on the right-hand side is actually true EMG that's been recorded from subjects. And you can see that below the zero SNR, you get more or less good accuracy, which makes sense because there is no noise in the, or there is very little contamination as you go above the 0 SNR. Okay, so we have done identification. Now let's quantify it. And why is quantification important? Because quantification is also going to inform us of which type of mitigation techniques to use and how much do we need to use of it. As an example here, here's a clean signal, and on the left-hand side and on the right-hand side, this is ECG that we've already identified that has contamination. 2, we have identified the type of contamination to be motion artifact, and 3, now we have identified it's at negative 15 dB SNR of the signal. So there have been few techniques that have been developed in this area. So some of them are based on SNR estimation. So we're trying to estimate what's the signal to noise ratio of the signal with the contamination as part of it. And another one is multi-level labeling. So multi-level labeling is saying the signal, whether it's good, not only saying a signal is good or bad, but saying a signal is good, acceptable, okay, and bad. So we're adding more levels. It's not black and white anymore, it's gray. So we're adding more gray levels in the between. Some of them have been based on machine learning, others have been based on templates, which is very similar to the previous technique we saw. You can see the results are quite high and quite very promising. We're gonna go through one technique. We're gonna go through the estimated SNR. So Quesnel proposed 4 different SQIs, and SQIs here are signal quality indices, to estimate the SNR of the signal in order to gate false alarms. Here are the different SQIs, or the 4 SQIs that he has proposed. So we have the mean, median, 25th percentile, and the minimum. And just a little bit of context, this is the signal quality, or the average SNR over a window of ECG. So let's say we have a window of 30 seconds. How can we best estimate the SNR of that window? Is that we're gonna take the mean of the SNRs that have been calculated for every single beat in that window, in the case of ECG here. The median is the median SNR, and then we have the 25th percentile and the minimum. Now, how is the SNR is being estimated for every beat? Well, actually, it's done through, again, templates and template subtraction. So on the left here, you see an ECG, multiple ECG beats overlaid on top of each other, and they've been averaged to generate the red signal. And you can see that the red signal is very representative of a typical ECG signal, which is the PQRST. On the right-hand side, you see ECG that has motion artifacts built into it, that has been added to it, and then that averaging happening. And you can see that the averaging also generated a typical PQRST template. Now, since we have the templates that are very similar to what a PQRST is, that means if we subtract that template from every single beat, then the information or whatever is left could be considered as noise. And by doing so, we could calculate the SNR, because now we have the signal, which is technically the template, and we calculate the power of that. And then we have, if we subtract the template from the signal, then we end up with what's left, which is essentially noise. And then we calculate the power of that, and then we would have signal to noise ratio. Here's a different ECG signals that had different levels of noise, and you can see at the negative 10 dB, it could be quite hard to discern the R peaks, but it's quite destructive. But we were able to discern the different fiducial points in order to generate the templates. Versus at 10 dB, it's quite clean. Here are the results. We could see that the SQI on the y-axis versus the SNR that has been calibrated in order to achieve a certain SNR in the signal, we could see that there's a nice linear correlation between the SQI and the SNR. And the left-hand side is with actually a morphological changes in the signal, which is the ST deviation. And on the right-hand side, on the left-hand side, there is no morphological changes. On the right-hand side, there is a morphological changes with the ST deviation. So one thing to highlight is that the 25th percentile SQI had the most similar noise estimation to the actual between the SQI and the SNR. And this actually can be seen here in these graphs. So you'll notice that the correlation for the SQI, 25th percentile SQI, is actually quite high compared to the others. And that's why this was chosen as an estimate of the SNR in the window that we're choosing. So this is estimation of SNR. Now next step is, well, let's mitigate it. So far we have seen detect noise, identify the noise, quantify the noise, and now let's mitigate it. And this is essentially going from that very bad signal, motion artifact, to the clean one. There has been a lot of work done there. You have your typical filters, you have your FIRs, your IIRs, you have And then you get a little bit fancier, and now you have adaptive filtering, which is able to target the noise itself. And then finally, you get super fancy, and then you get actually transform and source separation based. So you try to separate the sources of the signal that you have, and then from there, zero out the noise or what you think is noise, and then you would reconstruct it. These are some sample. And again, there's a lot in the literature here, some techniques that are as an examples. The first ones through filtering, they've used Kalman and adaptive filtering. And we were able, as an example, Ruhalva was able to achieve a delta SNR, which means an improvement in the SNR that's around 8.5. Milanesi was able to achieve an error between the post-filtering and pre-noise signal of 0.45, so quite low error. In the more source separation based techniques, you have Young and Mjovic, and you can see they've done it actually more on EEG and EMG, and that's actually more, you would find that more in the literature where the source separation are typically applied to the complicated techniques that don't have any discernible fiducial points, because we're not able to achieve or find out which parts of the signal that we want to remove or which parts we want to maintain. So Young used a morphological component analysis, achieving again a high correlation between, or achieving an acceptable correlation between a signal post-processing or post removing the noise and pre-adding the noise. Mjovic used EMD, empirical mode decomposition, plus independent component analysis, and was able to achieve a residual RMSE of 64.79%. And we'll jump into one of the techniques. So Manis used adaptive filtering to remove motion artifacts from ECG and compared with instantaneous and convolutional ICA, independent component analysis. So instantaneous ICA, we do the assumption that all the sources, all the signals, the noise, the contamination, and the signal is achieving the sensor at the same time. Versus in convolution ICA, we're not doing that assumption. It's actually more adaptable to the to biosignals, considering that our body has different filtering effects depending on the frequency of the signal. That's why it's not reaching the source at the same time. They decided to use an adaptive filter, and they used the accelerometer as a reference signal. Again, this is a very standard adaptive filtering. You get but here's the interesting thing is that they're using an accelerometer in order to model or as a substitute for the noise signal. And you're able to use it and you adjust your adaptive filter in order to achieve a filtered ECG signal. And when compared that with the ICA, they're able to achieve the error mean. And the error here is essentially it's a ratio of the difference between the signal post-processing and the signal before adding noise to the signal with the difference between the signal and the noise. And you're able to achieve very nice errors as percentage of 0.45 and 0.15 compared to, as an example, the ICAs. So to conclude, we've seen 4 different aspects of signal quality. We've seen detection, which tells us whether or not there's contamination on the signal. We've seen identification, which tells us what is the contaminant. We've seen quantification, which tells us how much is the contaminant, and finally how to mitigate it. Now, the first 3 steps are important in order to know how to mitigate the contaminant, or whether or not we even need to do mitigation of the contaminant. Again, if we're doing long-term monitoring, it may not make sense to waste computing power and power, especially that now we have low-power devices doing a lot of doing the computing part on trying to mitigate noise. That when we can, whether throw away the signal and collect it again, or wait until we have an acceptable signal before making any decisions. And this tells us that yes, we can do mitigation. However, we might want to consider doing some detection or doing identification or quantification first. Thank you.